Hello, everybody. Tom Barlow, Professor Barlow here. Physics 215 for Northampton Community College, calculus-based physics. So we're going to be doing chapter 12 today. And what's important to talk about with chapter 12 before we even get started is that most of you who are going to be going for any engineering degree, you are going to be taking an entire semester on this chapter subject, statics or static equilibrium. So in this chapter, we're going to talk about static equilibrium, elasticity, and fracture. So most of the structures that you encounter on a daily basis, whether they be bridges, skyscrapers, just a regular house, you use these methods of static equilibrium to solve for things like reaction forces and what different components or members of that structure are undergoing in terms of forces applied and how they're reacting to those forces. So up to this point, most of the stuff we've dealt with motion, kinematics, dynamics. So in this chapter, we're going to be dealing with statics. So basically in this chapter, we don't want things to move. You don't want your bridge to move. You don't want your building to move unless it's in an earthquake scenario. So it gives a little bit of flexibility. But in general terms, static is whatever it is staying still. And the other thing is that for anybody doing an engineering degree, you will do an entire semester on this subject. So hopefully this is a good starting point for you to get started on that class. So we're going to talk about what the conditions for equilibrium are. We're going to do some problem solving with statics. Then we're going to talk about stability and balance, elasticity, stress and strain, fracture, and the last two sections on trusses and bridges and arches and domes, I'm going to gloss over pretty quickly. And, you know, if you're going to be taking an engineering degree, I'd recommend looking it over. It's not going to be on the test, though. So what are the conditions for equilibrium? So for something not to move, the first condition of equilibrium is that your sum of forces in the x direction, in the y direction, and in the z direction. So sum of all the forces needs to be zero. So an object with forces acting on it, but with zero net force, is said to be in equilibrium. So a book sitting on a desk is exerting its weight on the desk, but the equal and opposite force to that is the normal force. So let's do an example here. And one of the things that we're going to talk about kind of as we go with these problems is reaction forces. Okay, so we're not really looking at, in this example, the reaction force of the cord at the wall, but we will get into that in a little bit. So what we're looking at here is the tensions in these cords. So they want us to calculate the tension in cord A and cord B, so they're calling it FA for force A and FB for force B, that are connected to the vertical cord supporting a 200 kilogram chandelier. So now kilograms of mass, okay? Now we're also going to ignore the mass of these cords. So they've already converted this 200 kilogram force for us into 1,960 newtons. And they've also given us a little bit of a picture here about, you know, the X and the Y components of this. So opposite interior angles, you have this angle is 60 degrees. You can also say this angle is 30 degrees for us to be able to determine whether or not we're dealing with sine or cosine. So I'm going to switch to a whiteboard. And we're going to do this problem. So if you look at the forces, you have this FA, and this angle here was the 60 degrees. In the picture, here was the ceiling and the 60 degrees was here. But same sort of thing. This FA, right? And I want you to get into the habit of whenever you see a force and it is not parallel to either the X or Y or Z, depending upon how many dimensions we're given, I want you to get into the habit of, I want to break this into an FAY component and an FAX component. So I want you to get in the habit of breaking these forces down. Okay, so I'm not feeling artistic tonight. I'm just going to draw a big circle here and say, this is my chandelier. And weight is equal to mass times gravity. We're given a mass of 200 kilograms. And if you take your 200 kilograms and multiply it by 9.8, so here's your mass. The weight of this chandelier is 1,960 newtons. But then we also have this FB, but FB is just in the X direction. There is no Y component to it. So it doesn't matter what order you work in. You can sum forces in the X first, or you can sum forces in the Y. If you have too many unknowns, try and solve for the other one. So previously what we did was sum of forces is equal to mass times acceleration. But we don't want anything to move in statics, so your sum of forces is going to be equal to 0. So I'm going to do the Y direction first. And I'm going to break this FA force into its Y component. So its Y component would be the sine of the angle that we're given. So it would be FA times sine of 60 degrees. And as you can see, that's positive. So keep track of your signs. Minus the weight of the chandelier is either the 200 kilograms times gravity or 1960 newtons is equal to 0. And I've got my free body diagram here. Always get in the habit of drawing your free body diagram. You're accounting for all the forces acting on an object. On a test, I'm going to give you some sort of points if you at least give me a free body diagram. Okay. So if we want to solve for FA, FA is 1960 newtons divided by sine of 60 degrees. So FA is equal to 2,260 newtons. That's only part of it. They wanted us to also solve for the other chord, which is FB. And in order to do that, I'm going to sum forces in the X direction. So in the X direction, I have this positive FB force. Okay. and FA is going in the opposite direction. So I'm saying this is positive in the X and this is positive in the Y. So this is going in the opposite direction. So this is going to be FA cosine because FAX cosine is adjacent, sine is opposite. Okay. Cosine 60 degrees. And that's going to be equal to 0. Now, as I said, you can easily make this 30 degrees, right? And say it is, right, sine of 30. If we started with the X direction, you'd quickly see that we don't know FB and we also don't know FA. So we have too many things to solve for. We don't know what to put in there. But we do now have FA. So FB is equal to the 2260 that we solved in the first part. Cosine 60 degrees. Just moving that over to the other side. And if you solve that, you should get FB is equal to 1,130 newtons. So if you end up with too many unknowns, switch to, the other direction and see if you can solve it that way. Okay? I'm going to stop sharing this. I'm going to go back over to PowerPoint. So we just solved for those two tensions in those two chords. The second condition for equilibrium has to do with the subject we started talking about in the last chapter, and that is torques. Now, when you get to statics, a lot of statics texts will refer to torques as moments. This text continues to refer to them as torques. So the second condition of equilibrium is that there can be no torque about any axis. Whatever axis that is can be completely arbitrary. So the sum of torques has to be equal to 0. There can't be any rotation for this either. Okay? So sum of torques has to be equal to 0 also. So for this example, they're saying a simple lever, a simple machine, a simple lever. This bar is being used to pry up on a large rock. We're using a small rock as a fulcrum or pivot point where you're going to be rotating about, okay? So you have this little r and this bigger R, okay? So you're going to have a lever arm, okay? The force required at the end of the long bar can be quite a bit smaller than the rock's weight, mass times gravity, since the torques are what's going to balance in this rotation about that little lever. So this weight can be very high. This can be short. As long as you lengthen this lever arm out to give yourself more leverage, okay? If, however, the leverage is insufficient, the large rock won't move. If the leverage is large enough, meaning if this radius or lever arm is long enough. So you could increase the force or you can increase the distance out from the lever arm, right? So if you were to look at this, right, the force on the two sides balances. So I'm going to stop sharing this for a second and go back to a whiteboard. Right. So if you look at the picture that we had, you have this rock, and the rock has a mass times gravity, right? And you had this smaller rock and a lever arm, and here, this distance is a small r, and then the person is pushing down with some pushing force here, and this dimension is your lever arm. So sum of torques needs to be 0. Okay, so you have a torque here and a torque here about this small fulcrum. Okay. We need to, at some point with torques, assign a positive and negative sign. So in most statics classes, counterclockwise is positive. So this first, the large rock, okay, is mass times gravity times this little lever arm here. So that's going to be positive because about this point, it's going to want to rotate counterclockwise. This one is going to be negative. So you have this pushing force times that larger lever arm is equal to 0. So you can see that to move this, because I'm just moving this over to the other side, to move this, I can either increase my pushing force or I can increase the radius. If I were to take that smaller lever arm and divide it by the larger lever arm, so if I bring that over, I'm taking that pulling force and dividing it by whatever I'm trying to move. So this is the ratio of my levers. This is something called mechanical advantage. Okay. So how do you solve problems in statics? Well, statics problems are something that you have to get practice at. Okay, there's just no two ways about it. You need to do a bunch of them. It's like the first time you started doing derivatives and integrals. You just have to do the drill work and you have to practice. Okay, so choose one object at a time. Draw its free body diagram. What are the forces acting on it? Make sure you account for all those forces. Choose a coordinate system and resolve the forces into components. So anything going to the left should be negative, to the right's positive, up is positive, down is negative. And then your torques, counterclockwise is typically positive. So then write your equations of equilibrium. Sum of the forces in the x, y, and z, all going to be equal to 0. Sum of torques around any axis, around any point, is going to be 0. If you choose the spot where you choose to sum the torques about, you're going to simplify the problem, okay? Because if you pick a spot to sum the torques where the lever arms are 0, okay, you're going to get rid of a lot of unknowns. And then, of course, you solve the problem. So we'll get into being clever about where you sum moments about or sum your torques about so that you can have those torques cancel or the lever arm be 0 and you don't have to account for them. So here's an example. you have a board that has a mass of 2 kilograms. We're assuming the board has a uniform density, okay? So if the board has a 2 kilogram mass, okay, that force is going to act in the center of that board, okay? So the mass of the board's 2 kilograms, is a seesaw for 2 children. Child A on the left-hand side has a mass of 30 grams, sits 2.5 meters from the pivot point, P. Okay. 2.5 meters out. At what distance X from the pivot point must the other child, who has a mass of 25 kilograms, place herself to balance the seesaw? So I am not going to redraw this picture. All I'm going to do is, so I'm not going to redraw this free body diagram because the free body diagram is done for us, right? So mass of child A is here, mass of child B is here. They want us to find this distance. Now, if I'm not careful where I choose this point about, right, then I'm going to have too many equations or too many unknowns to solve for. So let's take a look at this example on a whiteboard. So I'm not going to redraw this, but what I am going to do is I'm going to start off and say sum of forces in the y is equal to 0. I'm not going to do sum of forces in the x equals 0 because there are no forces given in the x. So what do we have? We have the normal force where the seesaw meets the fulcrum. Okay, so that's going to be positive. And then we have the mass of child A times gravity, because that goes downward. And we have the mass of child B times gravity, and that's also downward. The other thing that I have is the mass times gravity of the seesaw board itself. So this is the first child, this is the second child, that's the seesaw, that's the normal force. So you have to account for all of these things. Okay, so at this point, so this is the first condition of equilibrium. So let's take a look at sum of torques is equal to 0. So we are going to sum the torques at point P, or that fulcrum. So you're doing weights, so it's mass times gravity. And then the distance is 2.5 meters out for child A to the left. And that child is going to create a counterclockwise rotation, which is going to be positive. Now the child on the other side, that's going to be negative because it's going to be a clockwise rotation. And for this, we don't know what her distance is from the end. And we're going to assume well, we're not going to assume for the for this balance point, okay, where this thing balances, it's going to be at 0 meters because they're telling us that's where it balances. Okay. Assume the board is uniform and centered over the pivot point. So then we also have the normal force, but that is also at a distance of 0. And that's going to be equal to 0 because the sum of torques is equal to 0. Now notice these two are going to go to 0 because of the location that I picked to sum my torques about. Okay. So mass child A, pretty much at any point in time, you can plug the numbers in, but all we're going to do really here is solve for the mass of child A. You can plug gravity in, or you can see that gravity cancels here. Okay. So mass of child A is 30 kilograms times 9.8. I'm going to bring this over to the other side. And child B is 25 kilograms times 9.8 times x. Well, now I want to solve for x. Oh, I missed my 2.5 meters here. That's very important. I need to bring this 2.5 meters down because that is my lever arm. Okay. So now I can see that the 9.8s cancel. If I solve this through for x, I get 3 meters. Right. Now I could have summed my torques about either child A or child B or some point along here, but what you'll quickly see is I won't know where that center of the beam is relative to, because this is 3 meters. I assumed my rotation about this point, so those two lever arms canceled. If I pick another point, that might not be the case. Okay. So if a force in your solution comes out negative, so FA here, we're saying is positive. But if you were to solve this through, okay, the way I did with some of torques and everything, and FA turns out to be a negative solution, if you're accounting for it in the problem as being positive and upward, if you get a negative answer, that just means it's going in the opposite direction. If you assume it's going downward and you get a negative answer, then it's going upward. So it just means it's in the opposite direction of what you chose. So don't worry about getting all of the signs right in your assumption. In the answer, it will give you, it will work out in the math. Okay. So the force exerted by a bicep. So if we have how much force must a bicep muscle exert on a 5 kilogram ball held in your hand, so at first with the arm held horizontally, and then B when the arm is a 45-degree angle. The bicep muscle is connected to the forearm by a tendon attached 5 centimeters from the elbow joint. Assume that the mass of the forearm and the hand together are 2 kilograms and their center of gravity is shown. So they gave us the center of gravity being 15 centimeters over. They gave us that this bicep force, the force muscle, is 5 centimeters over from this joint. And they gave us that this 5 kilogram ball is 35 centimeters out. Now, again, where you sum your torques about in this example, it could help you depending upon where you choose to sum the torques about. I'm going to sum torques about this point right here, FJ. So I'm not going to redraw the free body diagram. you can kind of refer back to the picture. But I am going to sum torques. I am going to assume counterclockwise positive, and I am going to do it about Fj, which is the force at the muscle joint. Okay. So the first force is the muscle joint, but the lever arm is 0 because I'm summing my torques about that point. So the next force over is going to be 5 centimeters, which is 0.05 meters. So you want to be working in newtons and you want to be working in meters. If you're given centimeters, convert it to meters. If you're given a mass, convert it to kilograms, and then get the kilograms with gravity to a force, a weight. Okay. So here I am going to have the force in the bicep muscle, FM, and that's going to be positive because that's going to be working counterclockwise. The next force I encounter is the center of gravity for both the arm and the hand. That is located 15 centimeters over, which is 0.15 meters. And they're telling us that the hand weighs 2 kilograms. And that's multiplied by gravity. So weight is mass times gravity. But this one wants to rotate clockwise around the joint. So this one is going to be negative. And then the next and final force is the ball that's in the hand. And that is 35 centimeters or 0.35 meters. That is 5 kilograms multiplied by gravity. 9.8 is equal to 0. That torque is going to be clockwise, so that is also going to be negative. So the only thing that I'm solving for here is FM. So at this point, it's algebra. So if you just rearrange this thing to solve for FM, you're going to get 0.15 times 2 times 9.8. And I'm moving this over to the other side, plus 0.35 times 5 times 9.8. Divide that whole thing by your 0.05 meters to get FM. You would need to exert a 400 Newton force in your bicep to be able to support your hand, forearm, and a 5 kilogram ball. So given this situation, they asked us, what if the arm is at 45 degrees? So this is part A. Okay, so 400 Newton force. Stop sharing that. Let's go back to the PowerPoint. So here's my arm and free body diagram. So it's already here for us. The second part, what about when the bicep is at 45 degrees? Well, you're going to end up with the same torques, right? You see how the distances aren't really changing? So in this situation, the same torque equation is going to give you the same 400 Newton force. It's not going to change. So now we're going to do, I think, 2 more problems where we sum the forces matters. One of the things we have to talk about is reaction forces. Okay, so what we have here is a sign that's hanging from this cantilevered hinged beam. Okay, and we have a wire, a tension wire tying back into the wall. Okay, the beam is 2.2 meters long, has a mass of 25 kilograms, is mounted on one side by a hinge, and the beam is held by this cable. The cable makes a 30-degree angle. The beam supports a 28 kilogram sign suspended from its end. So they want us to determine the force in the hinge, okay? And they also want us to determine the force in the cable, okay? So let's talk first about hinges and cables, okay? This hinge, all right, it's just like a door on a hinge. It's allowed to freely rotate clockwise or counterclockwise. So if I took this cable away, or if I cut that cable, the sign would rotate back towards the building and bang against the building because this thing isn't held in place rigidly. There isn't a torque to account for here, okay? There is a reaction force in the X and a reaction force in the Y for this hinge, and they're kind of resolving it into this FH, but you have an FHY and an FHX for this hinge, for the reaction force for the hinge. Because if you think about it, when you start pulling down with this sign, this hinge has to experience something, okay? It's equal and opposite, right? So you have the hinge and you have the cable both working together to support this sign. They want us to find out the reaction force for the hinge, sorry, excuse me, and the tension force in the cable, okay? So how do we get started? Well, we can look at sum of forces in the X and the Y, and we'll do that. But we also need to sum torques. Now, if we were to sum torques about the hinge, we would have the sign, the beam itself to deal with, the sign to deal with, and the tension in the cable to deal with. If we were going to sum torques about this end, we don't have to deal with the tension in the cable. We don't have to deal with the FX because it is in line with the end of the beam. We would just have the FY, the reaction force for the hinge in the Y direction to deal with. So I'm going to sum my torques about the end of the sign right here, right at where the sign meets up with the cable, okay? Now you remember with the hinge, we have an FX and an FY, but we don't have a torque because, you know, if we cut the cable, this thing is allowed to freely rotate about that hinge point or that axis. Okay, so we have everything we need. I am going to stop screen sharing and I'm going to go to a whiteboard. I'm going to clear this. So what are my conditions of equilibrium? Sum of forces in the X equals 0. Sum of forces in the Y is equal to 0. Sum of torques about any axis is equal to 0. I'm choosing the very end of that beam. And I'm also going to specify that counterclockwise rotations are positive. Okay. So we can sum forces in the y direction equals 0. So we have the force, the reaction force for the hinge in the y. We have the tension in that cable is also going to have a y component. We have the mass times gravity, and this first one, this lowercase m, is for the beam. And then we also have the mass times gravity for the sine, which is the larger uppercase m. Now, if we look at this, too many unknowns, right? We have the mass of the sine, the mass of the beam, we know gravity, but we don't know the reaction force in the y for the hinge or the reaction force for the cable. Well, that's okay. Let's take a look at sum of forces in the x is equal to 0. So in the x, we have the positive FHX, and we have the negative tension in the cable, and that's going to be equal to 0. Well, that makes sense, equal and opposite, right? Okay, but it still doesn't help us because we don't know either of those. So what we need to get us started is we need to sum torques. And like I said, I'm summing torques about the very end of the beam where the cable and the sine and the end of the beam all kind of intersect out at the far end of it. So we have this FH in the y direction, and it is 2.2 meters away. But the way I'm assuming the sine, it's going to want to create a clockwise rotation around the end of that beam. So the sine is going to be negative. And then the next thing I'm going to have is the weight of the beam, which is the lowercase m times gravity. And that is 1.10 meters away. And we go back and look at that, that is going to create a counterclockwise rotation because we're assuming that is the weight of that is acting down. So it's going to want to rotate counterclockwise, so that sine is positive. Now, out at the end of the beam, we have our tension in the y in the cable, our tension in the x in the cable. We have the weight of the sine in the y. But if you look, all of those lever arm distances are zeros. So there is going to be no torque because all of those distances are zeros. Those forces are there, but they're not going to generate a torque. So those are the only two torque generating forces in this problem. So that helps because now we can just solve for FHY. If I solve for FHY, I get 1.1 times the mass of the beam, which they gave us was 25 kilograms. Times 9.8. And that whole thing is going to be divided by your 2.20. So FHY is 123 newtons. So that's my reaction force in the Y direction, 123 newtons. Well, now from that, I can plug this back into this equation, right? My sum of forces in the Y. So I'm just going to plug that in here for this 123 newtons plus FTY minus, again, the mass of the beam, 25 kilograms times 9.8 minus the sine, .8 kilograms times 9.8 equals 0. So if I solve this for FTY, I end up with 396 newtons in the Y for the tension in the Y. So I have everything in the Y direction worked out. Pretty much all I need to do now is use trig to determine the resolved tension force, and then the from there I can solve for Fx or whatever we want to do. So we know from trig, tension in the Y, opposite over adjacent, is Fx or Ftx tan theta if I want Ftx, I would end up with my 396 newtons divided by the tangent of 30 degrees, because tangent is opposite over adjacent. So if I look at my two angles, opposite would be the Y, adjacent would be the X. Ftx is going to be 686 newtons, which is also equal to Fhx, (686 newtons). Now, if I want just the tension in the cable, right? Because I have this resolved into its X and Y forces. Okay. It's just Pythagorean's theorem. Ftx squared plus Fty squared. So 686 squared plus 396 squared. So Ft, just a little less than 800 newtons, 792 newtons. And you can resolve the hinge force into a resolved component. That's typically not necessarily reported as much. I mean, you can figure out the total force on it, yes, using the exact same method, just to make sure you don't have a shearing problem with that hinge. We'll talk about what shear is here in a couple minutes. So to summarize, I summed my torques about this end to get rid of make some of those lever arms be zero. I resolved this tension in the Y and tension in the X to get the total tension. Okay. Okay, the ladder. So if we have a ladder problem, okay, if you have a ladder resting up against the wall, the only reaction force that you have for the ladder at the wall is going to be the normal force straight out from the wall on the ladder, exactly like what you see here. It's not like a hinge where it's being held vertically, okay? They want to know if we have a 5-meter long ladder leans against a smooth wall, okay, so the wall is frictionless, okay, at a point 4 meters above the floor, the ladder is uniform and has a mass of 12 kilograms, okay? Assuming the wall is frictionless but the floor is not, they want us to determine the forces exerted on the ladder by the floor and the wall. So what they're telling us here is if this is frictionless, this is my only reaction force. If the ground or the floor is not frictionless, we are going to have a force here that's going to want to resist this ladder moving out. So the ladder wants to kick out in the negative X direction, but you have this reaction force FCX that's going to resist that. It's kind of like the friction, well, it's not kind of, it's the friction force, right? And then you have a reaction force in the Y. And then we have the weight of the ladder. Okay, so the ladder is resting against the wall. They're saying that the ladder is 12 kilograms. Okay, they're saying also that the ladder is 5 meters long. So here's my ladder here. The length of the ladder, so the length of the hypotenuse is 5. So you should be able to recognize from trig that this is a 3, 4, 5 triangle. If it's a 3, 4, 5 triangle, this point from the end point up the ladder along the hypotenuse would be 2.5 meters. But if this X sub 0 is 3 meters and it's acting in the middle, it's 1.5 meters from the end. Where do I want to sum my torques about for this problem? Well, I'm going to, if I sum the torques up here where the two walls meet, then I have to deal with my reaction force at the wall, one of my reaction forces in the Y here, not in the X because it'll be parallel and the lever arm will be 0, and FC. If I do it up here at the wall, at this point, I have to deal with the ladder. Now I have to deal with both of these forces, which I won't know. If I sum my torques about FC, okay, if I sum my torques about this point, then I only have two things to deal with because the X and the Y reaction forces, their lever arms are going to be 0. So I only have to deal with these two forces. So I'm going to sum my torques about this point here. This is what I was saying about it takes a little bit of practice to see a couple of these problems to recognize where is a good spot to sum your torques about. Okay, so conditions for equilibrium. Sum of forces in the X is going to be equal to 0. Sum of forces in the Y, 0. Sum of torques about any axis is 0. But I am going to go about point FC, and I am going to use counterclockwise rotation as positive. my X and Y coordinate system. X is positive that way. Y is positive up. Okay. Let's first look at sum of forces. Let's go in the Y direction. So all I have in the Y is my FCY and the ladder, because I don't have a Y component for the reaction force at the wall, equal to 0. But we were given the mass of the ladder as 12 kilograms. So FCY is equal to 12 kilograms times gravity, 9.8 meters per second squared. So FCY is equal to 117.6 newtons. If we do sum of forces in the X, I would have my reaction force for C in the X. The weight of the ladder doesn't act at all. So that's equal to the reaction, and you have the negative reaction force at the wall. So that makes sense. They're equal and opposite. Now, if I sum torques, and I am going to sum them about point FC, again, counterclockwise is positive. So I have the reaction force at the wall, which is 4 meters, times the reaction force at the wall, FW. So the next thing that I'm going to have is the weight of the ladder itself. The weight of the ladder itself is the 1.5 meters over, because this is a 3, 4, 5 triangle. The weight of the ladder is mass of the ladder times gravity. Now, the FC is going to create a clockwise rotation, so that sign has to be negative, is equal to 0. So if we solve this for FW, it'd be my 1.5 times 12 times 9.8 divided by 4. So FW is 44 newtons. We see that from this, reaction force C in the X is also going to be 44 newtons, equal and opposite. And I could resolve this into one force, but this, the Fx, is the only one you'd be worried about for calculating your friction. All I would have to do really at that point is give you the coefficient of friction, right? You have your 44 newtons in the X, which is the reaction force there. 44 squared plus 117.6 squared. FC is 126 newtons. Okay. Let's take a look at the next topic. So before we move off of solving problems, do some of the textbook problems and get used to trying to find the most convenient spot to some torques to simplify the problem so that the lever arms are zero. Stability and balance. If you have a force on an object are such that they returned to its original equilibrium position, it is said to be in stable equilibrium. So if you have a pendulum or a ball hanging from the ceiling and you move it and it has a tendency to want to go back to its original position, that's considered stable equilibrium. If, however, it tends to move away from the equilibrium point, it will find another equilibrium point laying, like in the case of this pencil, it will find an equilibrium point So if something tends to move away from its equilibrium point, because obviously a pencil is not going to balance on the tip of the pencil, in that case, it's said to be an unstable equilibrium. But what's going to happen is the pencil will fall to the desk or fall to the floor or whatever, and it will remain in a new position. It'll remain horizontal. That new position is now considered to be neutral equilibrium, okay? If we take a look at an object in stable equilibrium, you can tip it and get it into a situation where it is in unstable equilibrium. That happens when the center of gravity is tipped outside of the point that you're pivoting around or the point that you're rotating about. It will be stable again after it lands, and then it'll be a neutral equilibrium like we said. But as you can see, if I move this refrigerator, as long as, if I'm rotating it about this lower right corner, as long as that center of gravity is kept to the left side of that pivot point, it'll have a tendency to want to upright itself. As soon as that center of gravity moves just beyond that pivot point, now it wants to rotate the other direction. So people carrying like a heavy backpack or something, they tend to adjust their posture over their feet, and this can lead to injuries, of course, but what you're trying to do is get the weight over your center of gravity. Okay, so now we're going to talk about elasticity, stress, and strain. So Hooke's law is a pretty simple equation. It basically says that the change in length is proportional to the force applied. So the more weight that I put on this hook, the more that rod that's hanging down from the ceiling is going to want to elongate. This proportionality holds true up to a certain point, and that point is called the proportional limit. So if you look down here on the x-axis, we're plotting change in length or elongation and force applied. There's no infinite limit to this. What's going to happen is this is called the elastic region. And what happens here is you put the weight on and you take the weight off, and it's going to want to return back to its original position. Once you reach this proportional limit, you're starting to get to the elastic limit. The elastic limit from that point on, if you apply any more weight or force and you take that force off, it is permanently going to be deformed. And if you keep carrying it into this plastic region, it'll go through a phase called strain hardening, where it reaches the maximum force you can apply, and then there's a slight dip before whatever it is breaks or fractures. So the change in length of a stretched object not only depends on the force, it depends on the length of the material, the cross-sectional area of the material, and then there's a factor built into this called the elastic modulus or Young's modulus. So this is just a simple algebraic equation. Delta L is change in length, F is force applied, A is the cross-sectional area of whatever you're dealing with. L sub 0 or L naught is the original length, and then E is Young's modulus or the elastic modulus. It's also called a constant of proportionality. Okay, so on a test, you'd be given a table like this where you'd have to look up. We'll talk a little bit more about shear modulus and bulk modulus in a minute, but that proportionality constant, Young's modulus or modulus of elasticity, is used in this equation. You get it from here, and these are the different types of materials. Okay. So notice that the table goes down here to liquids and gases. You're not going to stretch a liquid or gas. Okay. So the tension in a piano wire. So if you have a 1.6 meter long piano wire and it has a diameter of 0.2 centimeters, how great is the tension in the wire if it stretches 0.25 of a centimeter when it's tightened? Okay. So this is really just using that algebraic equation. Change in length, 1 over Young's modulus, force over area, L sub 0. So the L, or the area of this, it's a circle, so it's pi r squared or pi d squared over 4. The radius, if it's 0.2 centimeters in diameter, it's a 0.1 centimeter radius, which is 0.0010 meters. So if you look at the units for that modulus, okay, the units are in, let's, if you flip back and take a look at it, it's Newton per meter squared. So you want to be working in units of meters and newtons. 10 to the minus 6 meters squared. So that's my area for up there. So my change in length they gave us, it stretches 0.25 centimeters, which is 0.0025 meters. So be careful you're working in the right units. The steel piano wire is 2 times 10 to the 11th Newton per meter squared. The force applied is what we want to figure out. The cross-sectional area we just did up top here, 3.14 times 10 to the minus 6 meters squared. The original length is the 1.6 meters, which was given in the problem. And if you solve this for F, you get a little less than 1,000 newtons, 980 newtons. So it's really just taking a look and being mindful of what your units are and looking up that value in a table. So elasticity, stress, and strain. Stress is defined as force per unit area. Stress is force over area, pounds per square inch. Okay, stress. Strain is defined as the ratio of the change in length to the original length. So if you rearrange that elastic modulus equation, elastic modulus is F over A, or change in divided by change in length over original length. E, that elastic modulus, is just stress divided by strain. Okay. So there are different forces objects can encounter. You have tension, compression, and shear are the most common. There's others, but the most common you're going to find are tension, compression, and shear. So tension is where you pull on the two ends of something and try and stretch it or elongate it out. Tensile stresses, the forces tend to stretch an object. Compressional stress is the opposite, all right? And it's the exact opposite of tension. You're squeezing something together. Okay, compression is squeezing together. Okay, like these columns here are under compression. So here are the three different types that we just talked about. You have tension, compression, and shear. Now, shear is where you apply two forces that oppose one another, and you're trying to get this type of effect happening. Okay. Shear strain, okay, notice it's basically the same exact equation, but you have a G value, which is your shear modulus. So back in that table, notice you have a shear modulus column, and you also have a bulk modulus column, but it's nearly the identical equation, right? But this is your shear modulus, okay? And then the last one, notice that they gave us values for liquids and gases, but they didn't report your shear modulus. They didn't report bulk modulus for liquids and gases. Well, that's because the bulk modulus deals with the liquids and gases. You can also have Young's, shear, and bulk for some solids, okay? So if an object is subjected to inward forces on all sides, its volume will change depending upon its bulk modulus. So this is change in volume with respect to original volume. So this really only applies to fluids, where fluids are either liquids or gases, okay? So delta V is change in volume, V sub 0 or V naught is original volume, B is your bulk modulus, delta P is the change in pressure or stress or force per unit area. So if it's a negative sign, volume decreases as pressure increases, right? So this negative sign here, volume decreases, pressure increases, and vice versa. So if the stress of an object is so great that it breaks, that's called fracture, okay? Ultimate strengths of different materials under tensile stress, compressional stress, and shear stress have all been measured. So in engineering, most of the time, you do not design something right up to its ultimate strength. You usually keep a third, a half, a tenth, right? That's called a factor of safety. You don't design right up to it because you don't want it to fail. Okay. So these are your ultimate strengths for different types of materials. On a test, it would be given to you. So if we want to use this in a problem, we're going to look at the same piano wire. Okay, it's 1.6 meters long, diameter of 0.2 centimeters. What tension force would break it? So I'm going to stop sharing and go to a whiteboard. So what force would break it? We have stress is equal to F over A. We know the cross-sectional area from before. We did this before, but just to quickly review, pi r squared. The radius was, sorry, the diameter was 0.2. So the radius is 0.1. Okay. And from the previous table, steel fractures in tension at 500 times 10 to the 6th Newton per meter squared. So rearranging this, force is equal to stress times area. If it breaks at 500 if it breaks at 500 times 10 to the 6 Newton per meter, .0 times 10 to the minus third meters squared. So you would have to apply 1,600 newtons of force to break that piano wire. Now, in the practical real world, you wouldn't want to put that piano wire in a situation where it was taking any more than, let's say, 800 newtons of force. And the reason for that is because of factor of safety. You do not want to put it in a situation where you're designing right up to the breaking point of whatever it is. One of the other things that we want to talk about is we have this horizontal beam, okay? This horizontal beam is actually experiencing something called shear, okay? A horizontal beam on its top surface will be in compression. On its bottom surface, it will be in tension. So it's got to be made of a material that can handle both the tension and compression. So there's shearing stresses that are occurring within this beam as a result of what you're seeing here with the tension and compression. Okay. So you're subjecting this beam to torques and generating internal torques on the material that the beam is made out of. I want you guys to research this on your own. And if you research this on your own and you send me a little bit of a summary of what is going on here, I'm not going to go through it, but in the late 70s, early 80s, there was a collapse in Kansas City at the Hyatt Regency. It was a hotel and it was a grand opening. And what I'd like you to do is there's two very good videos online where they talk about what happened with this and how something that it was on its surface looked like a simple substitution was not at all a simple substitution. So, and it happened during construction, but I'd like you to research this on your own, and I'll give you some extra credit points if you send me a quick email summarizing what it is that I'm kind of asking you to research here. I'm not asking you for a full-blown book report. I just want to see if you've looked into it yourself, okay? So fracture on a beam. You have a pine beam that's 3.6 meters long. Okay, it has dimensions of 9.5 centimeters by 14 centimeters is its cross section. It rests on two supports at its ends, and the beam has a mass of 25 kilograms. There are two vertical roof supports resting on it, and they gave the dimensions to those supports below. Each 1/3 of the way in from the ends. So what maximum load, FL, can each roof support exert without shearing the pine beam at its supports? So basically without breaking the pine beam, okay, what can it support? They want us to use a factor of safety of 5. Okay, okay, so let's figure this out. So I'm not going to redraw that picture because for all intents and purposes, that is our free body diagram. They want us to use a factor of safety of 5. What does that mean? They want us to reduce the amount of force that we're applying to this thing by 1/5. So I'm going to reduce by 1/5 my stress times area. Okay. So it'll be 1/5. The pine can handle, and this is just a lookup from the table that I had. It's 5 times 10 to the 6th Newton per meter squared. Now notice I'm dealing with meters and newtons. So if you're given masses, you have to convert them to kilograms. If you're given masses, you have to get them to kilograms and then get them to forces in newtons. And if you're given centimeters, you have to convert those to meters. So if this thing is 9.5 centimeters, it's 0.095 meters. 14 centimeters is 0.14 meters. So the force that we can apply up to 13,000 newtons. So now what I need to do is figure out what I can apply. So I'm going to sum torques about some point has to be equal to 0. So you can pick which end of the beam you'd like. I'm going to choose the left edge of the beam. So I've got one of these roof supports, FL. That's 1.2 meters away. But that's going to create a clockwise rotation, so this has to be negative. Then I have the weight of the beam itself, the 25 kilograms times my 9.8, and that is halfway across, which is 1.8. That is also going to create a clockwise rotation, so this is negative. Then I also have a second FL, not a third, a second one. And this is 2.4 meters. That one is also negative. And then my last one is the reaction force at the end, at the far end of the beam. That's 3.6 meters away. But that one is going to create a counterclockwise rotation, so that's positive. And this whole thing is going to be equal to 0. So if I solve this, I get an FL is equal to 13,000 newtons. But I have two of those, right? One at each location. And they wanted us to figure out what maximum force FL, so that's the 13,000, right? So we have 2, it's 13,000 divided by your 9.8. So each one can support 2,600 kilograms. So now the text goes into talking about trusses and bridges, all of which are very interesting. But these are sections in the text that are asterisked, so you are not required to know this material for the test, but it is a good preview of what you're going to see when you take a class in statics. So you're going to be dealing with roof trusses or bridge beam trusses and solving for each of the components of that truss, which are called members. So each member of the truss is either going to be in tension, compression, one or the other. You always assume that they're in tension. So you do all of your calculations assuming they're in tension, and if you get negative forces on any particular component, then you know it's in compression. Right, so you can go through and do free body diagrams and solve for each of the components of that using just simple equations of equilibrium. Sum of forces, sum of torques, all equal to 0. Do it at each of those pins, at each of those locations, and you can figure out what each of the components of that bridge are experiencing. Larger bridges, you have suspension bridges or arched bridges, arches and domes. Romans used the arches a long time ago because of the distances that they could span, right? The stones or brick are mainly under compression, which tends to make it a bit stronger. We started making things too big at one point, and they ended up using something called flying buttresses to help push back and counter some of the large forces that they were encountering. So for an object at rest, it is said to be in equilibrium. The study of such objects is called statics. In order for an object to be in equilibrium, there must be no net force acting on it. There must also be no net torque about any axis. An object is in static equilibrium, can be stable, unstable, or neutral. Materials can be put under tension, compression, or shear forces. If the force is too great, the material will exceed its elastic limits and it will deform plastically. If you keep deforming it and you keep applying force, you could take the material to the point where it fractures or breaks. And that is the end of chapter 12. So there will be some recommended homework problems from this chapter, and there will also be a lab for this. Come to the Zoom meetings prepared with questions. And this is the last chapter for Unit 3. And we'll get started with Unit 4. We'll pick up with Chapter 13. So we'll talk soon. Email with questions. Come to the Zoom meetings prepared with questions. Thank you and have a great night.